Hi guys, so I am going to go ahead and walk you through our first topic for Unit 3. If we remember, let me go ahead and present this. Sweet, okay. So, Unit 3 is all about intermolecular forces and properties. There are 13 subunits or topics, so it is a rather large unit, but never fear. I'll keep making these videos for these topics, and hopefully that'll aid and help a little bit. So intermolecular, remember, we're studying the forces between molecules, not within a molecule itself. So intramolecular forces are the interaction within a single molecule, and intermolecular forces are the interaction between two different molecules. Intermolecular forces also abide by Coulomb's law, but they're much, much weaker than within a molecule itself. Okay, so here are all 13 of our topics, but the only one we're going to focus on today is the first subunit, which is intermolecular forces themselves. It's a little introduction on the different types of intermolecular forces, just to give you a base understanding of the forces that we're going to be discussing once we look at the rest of this unit. So, if you guys remember, this is our periodic table, and it's displaying the electronegativity of the atoms themselves. If we can see as we move up from the bottom up of the periodic table and from left to right, that electronegativity value is increasing. So our lowest electronegativity value is over here with francium in the bottom left corner of the periodic table. And then the element with the greatest electronegativity is fluorine over here in the top right corner. So these are going to be crucial when discussing intermolecular forces, because that electronegativity is going to help determine the polarity of our molecules. All right, so here are some of the main forces. These are the main ones that we are going to be focusing on for this discussion today. So type number 1 is a dipole force that is between two polar molecules. A dipole-induced dipole is one polar and one nonpolar molecule. Typically, that polar molecule can persuade the nonpolar molecule to shift its electrons around. And so when I say shift electrons, let's assume that this balloon is our nonpolar. So if you were to have a polar molecule, it's upside down, I'm so sorry. There we go. If you were to have a polar molecule, you would have a smaller end, which is your positively charged side, right? Because this is where our nucleus is, and then our electrons, which have the negative charge, reside in the larger part of the molecule. And so if we were to have a nonpolar molecule, it would be more rounded in shape in general. But in the case of a dipole-induced dipole, the polar molecule, can actually cause a shift in the electrons within a molecule. And so keep in mind, electrons aren't stagnant, right? They're constantly moving, and molecules, the electrons, can actually shift around, much like how I can shift the air inside this balloon. So that polar molecule can actually cause the electrons to shift a little bit, so they can actually turn into a temporary polar molecule. The dipole-dipole is a situation where the electrons are permanently fixed in a polar situation, but with an induced dipole, they are temporarily shifted. We'll explore more on that in a minute. The nonpolar molecules are actually more commonly referred to as the London dispersion forces, or van der Waals. They're interchangeable, but I'm going to be discussing them as London dispersion forces. The electrons inevitably shift, right? Those electrons are moving around, leading to attractions between neighboring molecules. So even if your molecules are all nonpolar, right? If they're all nonpolar and circular, those electrons, again, they're not stagnant. They're constantly moving around. And so eventually you will have a molecule or two that their electrons shift at the right time, and Coulomb's law comes into play, where your opposite charges will attract and form that collective force between them. And then lastly, we have hydrogen bonding. See how it's in quotes? It's not actually a bond. And this is between hydrogen and one of the Fon elements. I've got to move myself. I wonder if it'll let me. No? Maybe. Oh, that's not it. Okay. Well, I'll make sure to adjust that. But it's between hydrogen and one of the Fon elements, which we'll get to in a little bit. So first thing, let's go ahead and look at dipole-dipole. So this is the most straightforward of the bunch. It occurs between two polar molecules. Here we have hydrogen chlorine right here. These are two polar molecules. You can see that attraction between the negatively charged and positively charged sides of their molecules. This can be either attractive or repulsive, and the molecules will orient themselves to maximize that attractive property. The greater the dipole moment, the greater the interaction. So the more polar your molecule is, the stronger that attraction, the stronger the interaction between the molecules. Some examples of these types of forces include carbon monoxide, nitrogen trifluoride, and then, oh my goodness, I'm blanking, this molecule here as well, right? So they're stronger than London dispersion forces, which we're going to get to. We already said that those are between non-polar molecules. And these occur when electrons are permanently distributed asymmetrically in a molecule. So we have typically a shift like this balloon where your electrons are typically permanently fixed on one side, causing that polarity. So one end will be positive and one end is negative. All right, then we've got dipole and induced dipole. We're not going to spend too much time on this because it's essentially the same as a dipole-dipole, only one of them was coerced into being a dipole. So the dipole is temporary and relies on the orientation. So it's always an attractive property. So let's say we have this O2 molecule and water. So water, these lone pair electrons can actually cause a shift in the electrons of that O2 molecule to where they shift to one side. It repels that like charge, shifting the electrons to one side and attracting that nucleus, that dense positively charged nucleus towards itself. Again, these lone pair electrons from this polar molecule will repel the like charged electrons and attract the oppositely charged protons in the nucleus. All right, LDF, otherwise known as London dispersion forces. So these are nonpolar molecules interactions, the electrons still fluctuating randomly in the molecule. So again, you've got your nonpolar, but those electrons are still moving around and still shifting. And when they do this, it produces temporary dipoles. And when the temporary dipole of one molecule approaches another molecule, if it just so happens to line up, the electrons disperse away from the negative dipole, and this creates another temporary dipole, and they end up attracting towards each other. It's a net attractive force, and therefore they are joined together then. Not in a bond, of course. It's not as strong as a bond, but that's basically the essence of it. So let's say both of your molecules look like this, right? They're that spherical shape. And so they actually will shift around randomly, of course. So if your electrons are shifting around, let's say they end up on this right side of your molecule and your nucleus ends up on the left by happenstance, and you see another molecule that's lined up the same way on that opposite side. So your electrons and your nucleus from the other molecule will attract and it will repel the other neighboring electrons so that there is that dipole there. Right, London dispersion forces exhibited by all molecules, even polar molecules. So even in a polar situation where you already have your electrons shifted around, these forces are present in any type of molecule. So if you're encountered with a question asking, oh, well, what intermolecular forces are present here? Your answer will always have London dispersion forces listed because it's present in every type of molecule. They are the primary type of interaction between nonpolar molecules, already covered that, and the strength of the LDF depends on how easily the electrons can disperse. So the easier it is for your electrons to shift around and to move, the stronger the dispersion forces. So the larger the cloud, the more polarizable and the greater the strength. So think about it. If your molecule is huge, there's a lot more space for those electrons to move around and to bounce around and to shift. And if that's the case, the chances of them shifting to a different place and meeting up with another molecule that they have that attraction and repulsion towards is a lot greater if your molecule is larger. If it's smaller, those electrons don't have as much room to move around, so it's less likely that your forces will be as strong. So let's actually look at a couple molecules here and kind of compare and see and practice differentiating between the two. So we've got butane and 2-methylpropane. Sorry, it always takes me a minute to read them, but we're good. So we've got two molecules. They actually have the exact same chemical formula. It's C4H10. They have the exact same one, but they're actually structured just a little differently. And butane's boiling point is negative 0.5 degrees Celsius, and 2-methylpropane's boiling point is negative 11.7 degrees Celsius. So there's a little difference in that boiling point there. So one thing I want you guys to look at, go ahead and pause and look at these structures. Look at that boiling point. Make note of differences you see. Okay? So again, same formula, the electron clouds are comparable in size. So if you're dealing with two molecules that are very similar, their electron clouds are going to be similar in size. So you cannot use the size of the molecule as a tool to figure out which forces are stronger. Now, if we look at butane, it's more linear, right? It's more linear. That means that there's a greater surface area for contact between molecules versus 2-methylpropane. You've got to think of it like a puzzle, right? So if we've got a long, skinny piece versus a like triangle-shaped piece, it's going to be a lot easier for this long, skinny piece to find other pieces of the puzzle to connect to, versus a triangular piece, which might have a harder time. There's not as much surface area there to connect and interact with other molecules. So butane is going to have the greater forces. Another trick, which we'll get to later, is the boiling point. Butane has a higher boiling point, and its higher boiling point shows us that it is more resistant to phase change. And by resisting that phase change, that means that the forces between the molecules are stronger. It doesn't want to change. It doesn't want to separate. It likes where it's at. It takes a lot more force to change. Okay, now these are going to be our strongest. Well, fairly strong bonds. These are hydrogen bonding. And I do the quotation marks because, of course, they're not actually bonds because they occur between molecules, not within a molecule. So this type of force actually explains the unusual strength between water molecules. So it's a special case dipole-dipole situation, actually. Highly electronegative oxygen draws itself electrons from the hydrogens. So this actually causes hydrogen to expose a bare proton. So oxygen can actually draw hydrogen's electrons towards it, giving it a overall negative charge. And so what occurs then is that negative charge attracts, it attracts this bare proton then from another water molecule. And if you guys see this little red dotted line here, that represents the hydrogen bonding. It's a very strong dipole polar attraction between these molecules. So this only occurs between hydrogen, which is covalently bonded to one of the FON elements, FON. That stands for fluorine, oxygen, and nitrogen. And it only occurs between those three because they're the three most electronegative elements. So if we see here, fluorine and oxygen are covalently bonded here. So when we see that, and we see that here too, we know that this is a hydrogen bond. And This is just the lecture piece of the video, so following this later on in these slides, you'll be able to actually practice this a little bit, and hopefully that will further enhance this experience, because it's kind of hard to explain without actually practicing. So make sure you go to the practice slides after you watch this video. And then another type of intermolecular force is the ion dipole. So this is when an ionic compound dissolves and the dipole interacts with the ions of the compound, forcing them to separate. So this is salt water, right? We have sodium and chloride that have actually been separated, and we've got the water molecules floating around those. And you can see that the intermolecular forces have caused the negatively charged oxygen side of the water molecule to be attracted to the positively charged sodium ion. And then vice versa over here with the negatively charged chlorine, you've got your positively charged hydrogen atoms attracted towards it. This can be stronger even than hydrogen bonding, which accounts for boiling point elevation of a solution, which we're going to get to solutions a little later on in this unit, so don't worry about that too much yet. Just understand that when you've got this ion and dipole bond, that can be your strongest type of force. It can for sure be stronger than hydrogen bonding, which is strong enough as it is. So let me roll on. So here is a really good graphic that actually explains and gives you a very good visual of these different types of intermolecular forces. Starting at the top up here with ion dipole, that is your strongest force. And then as you go down, these intermolecular forces get weaker. Now, if you'll look, you see the range of their force strength. And the most interesting one is down here at the bottom. It's your London dispersion force. It's got a huge range. You can see it can be your weakest type of force, but depending on the size of the electron clouds, if you've got really large electron clouds for your atoms, you can actually have a great deal of force between your nonpolar molecules. And that can actually lead to a stronger force than dipole-induced dipole, ion-induced dipole, dipole-dipole. It can come all the way up to hydrogen bond level strength. Also, I want you guys to see this. So this is a great resource I recommend looking at as well. You can actually watch simulations of these different types of forces. So we're going to start with dipole-dipole. So I want you to watch. You can see the different charges, the negative and positive charged sides of the molecule. So watch what happens. As the molecules shift around, you see the positive and negative attracted to each other. Cool. Then if we go to London dispersion, we've got two different nonpolar molecules, and you'll actually get to see the shift. See, there's the shift. Opposites are repelled, and alike charges attract. Pretty cool. See those electrons shifting around? And then last but not least, we've got hydrogen bonding. Of course, this is going to be represented by your water molecules because this is one of the most prevalent compounds that you will see it within. You see those covalent bonds between the oxygen and hydrogen. Again, it's a dipole-dipole force, but it's even stronger because it is aligned with the Fon elements and their covalent bond with your hydrogen. So now we need to look at properties that actually increase as your intermolecular forces increase. This is how you're going to be able to actually analyze different compounds and see which has stronger forces, what impacts that force. These are going to be the tools you need to answer these upcoming practice questions. So, some properties that increase as your intermolecular forces increase, your melting and your boiling point, right? So, like I said, it has to deal with the force's resistance to phase change. So, keep in mind, the stronger the forces are, the less willing they will be to shift from one phase to another. Melting point, right? Going from solid to liquid, boiling, going from liquid to gas, that would involve your molecules spreading apart. Because think of a solid, right? Solid, your molecules are like rigid. They're in that crystalline structure. They're all lined up in a certain pattern, locked into place. And if you move them apart, you're moving to a liquid and then a gas. Those particles are moving further and further apart. And so having a higher melting and a higher boiling point is like a resistance to that almost. Like it needs more and more energy to shift to a different phase. In particular, moving from a solid to a liquid to a gas. Also, surface tension, the ability for the surface of a liquid to resist an external force, viscosity, which is the resistance to flow, and then heat of vaporization, which is energy required to evaporate a substance. On the flip side, you've got properties that decrease as your intermolecular forces increase. That includes vapor pressure, which is the pressure exerted by a gas when it's at equilibrium within a container with its liquid. So if you have a gas with a liquid in a container, that's the pressure that the vapor is pushing on the container itself. And then volatility is the ease of evaporation as well. That decreases. So again, it's making it harder to evaporate. So while volatility is the ease of evaporation, of course, that's going to decrease because evaporating is going to be more difficult. Okay, so finally, if the size of the molecule is comparable, similar atoms, similarity, so your atoms themselves look fairly similar and your electron clouds are very similar in size, just remember that your hydrogen bonding is the most strong, right? Except for your ion dipole, but that is a random exception that we will not see as much. Your hydrogen bonding is the strongest bonding, dipole, and then your London dispersion forces. However, that's just a general statement. It really depends on the situation. Molecules vary in size, and that makes it more difficult to determine your London dispersion forces, because if your molecules are huge, it can actually be stronger than your dipole and even your hydrogen bonding. So you always have to look at the size of your molecules first. And then if they're all the same size, then you can follow this general assumption. Hydrogen bonding being the strongest, London dispersion being the weakest. So I think, yeah, that's it. So this is just a basic intro for intermolecular forces. Hopefully you guys got a good idea over the main different types of forces we're going to be looking at in the future. Again, this is mostly understanding terms and the concept of them. So feel free to rewatch this video, tune in to our live class so you can ask questions, but make sure you go practice the problems at the end of this slideshow as well. So let me know if you guys have any questions, and have a good day.